Okay, hello everybody. I hope all of you are fine and doing well. So, attention please, everybody. Okay, so today we are going to talk about another series of algorithms that is one of the famous branch of algorithms named policy gradient. If you remember last week, we talked about the deep reinforcement learning and we saw how we can bring the function approximation with replacing deep network and placing the Q network and merging them together in order to estimate the Q value and value functions in order to solve problems. But today we want to see, okay, uh, what else we can do? Is it always reasonable to work with value function, or we can do something else instead of using value function? So the reason, because of that, we will see policy gradient algorithms. There are many different techniques. We will see some today, and we will see how they are strong in solving problems and what are the general weaknesses of those techniques. So today we will focus on the policy gradient. First of all, we will define it, how it is, and what is the motivation. Then we talk about the reinforced algorithm, one of the most basic algorithms for policy gradient. After talking about the reinforced algorithm, we will talk about the vanilla policy gradient. We will see how similar it is to the reinforced and what are the differences and how it is performing. Then we will see different policy gradient methods to update the parameters. So we are not only limited to one technique, like two techniques like reinforced vanilla. Instead, we also can replace the updating the parameters by policy gradient technique. After that, we go through the Actor-Critic algorithms. We will see, okay, how we can bring the benefits of policy gradient with the already known uh, value function approximation. We will try to merge them together. Finally, we will have a look at the most recent algorithms that is commonly used as proximal policy optimization, as known as PPO. There are multiple different versions and different implementations. We will see just the baseline, and we will see how the general idea is working there, and what is the motivation that if you want to implement what you need to do. Before starting today's course, do you have any question about previous topics? And also, better to mention, after we finish these slides, I ask your TA to come and introduce you at the last part of class, introduce the Isaac Gym simulator for you that you can perform the studied algorithm there on GPU. That will be a brief introduction of the simulator that in future, if you want to develop algorithms that can be performed faster, like the algorithm that you're training in 12 hours, 10 hours can be reduced to 1 hour based on performing on GPU. So if there is no question, we can dive into details of today's course. First of all, let's see what is the policy gradient. Before also starting, I want to mention almost most of the topics that we studied so far from beginning are going to be directly or indirectly used here. So all the concepts that we discussed, different algorithms are going to be engaged here, and you will see how beneficial were. If you remember, I mentioned that in the reinforcement learning class, understanding the basics are more important than learning the big algorithm. Because if you know the basics, when you study yourself even can easily understand what's happening. And today you will see based on flow of the info that we have. Okay, be careful. We don't want injuries in class. Later, our class will be famous that this class has injuries. So what is the policy gradient? First of all, in reinforcement learning, what was the main objective? The main objective was finding optimal policy for the agent to maximize reward. So our agent is trying different actions in the environment. We wanted to find best policy that finally we collect maximum possible reward. This was the general idea that we had. So now we're saying, okay, in policy gradient techniques, we want to also solve the same problem, same reinforcement learning problem. But here, what we want to do, we want to, instead of working with value function, we want to directly optimize the policy. What does it mean? It means that we don't want to calculate the value anymore. So we had two kinds of value, state value and action value. That one was considering the actions per each state, but one was calculating only value for per each state. But now we are trying to find a way to not calculate the value, just directly work with policy itself and try to improve and optimize the policy itself. And what was the policy? The policy was saying, like, in this state, if I discrete action, if I have discrete actions, move forward, right, left, back, I want to improve this directly, not rely on calculating the value actually anymore. That this idea, this motivation, opens a range of different techniques for us. So we say in policy gradient, we usually model the policy with parameterized functions. So now you should think that when we want to parameterize the policy, we actually, what we did with parameterization, we use, for example, neural network in order to calculate some weights. Now we want to do the same calculation of weights, but on the policy, and we will see how today. We are not, of course, limited to neural network or deep learning, but that's the best option that we have for policy gradient series of algorithms. So, as I mentioned, we don't want to calculate the value function directly, but actually we say a value function may still be used to learn policy parameters, but it is not required for action selection. We will see that, okay, to evaluate kind of the policy, we need to have some calculations. It's not like from air that this action is good and better than the other action. We need to have some calculations, but we don't want to rely on specifically value function approximation. And the reason will be clear soon for you why that's the that's we want to avoid it. Although we're calculating, we don't want to optimize based on the value function directly. So last week, we've had a look on the different reinforcement learning algorithms. Let's see what's happening and where we are. Already, we discussed the model-based techniques in beginning of the class. In the model-free techniques, also, we discussed Q-learning itself. But last week, most importantly, came to discuss the deep Q-learning. And we saw that also it is capable, and in some applications, it does very well. But on the other hand, now we want to move toward the policy optimization. And in policy optimization, one of the initial and base algorithms that we have is policy gradient. So we will start with discussion and seeing how policy gradient idea is and how we can formulate it. Then we try to see one basic algorithm of actor-critic over here. And we have too many algorithms here, like maybe over 50, 100 different. But I will try to today cover the basics of the important ones. Policy gradient, one technique of Actor-Critic. We have PPO that is very similar to PPO, but it is very complex to implement, and because of that, almost no one tries to use it, and directly people go to use PPO with same performance, less complexity. So I also will try to show what is it and what is happening. One note, maybe in future, next semester after next semester, I will open deep reinforcement learning that requires one full semester. If you study your book also, it is stated that for reinforcement learning, we need two semesters to cover all the topics. Because of that, I may open later, a semester after next semester, to in detail go to the deep reinforcement learning and see how they are exactly working. So, is it clear? No question so far. So we've seen this part. We want to see that part. And these algorithms over there, also there are variants that they are trying to merge this and this technique together to propose other solutions for example, continuous action space that I will also talk about it today. Or more multi-agent version of the learning based on the deep reinforcement learning. So in policy gradient, with value-based approaches, we say we want to, what we were doing in value-based approaches, we were choosing actions greedily. So we were calculating values, first of all. After calculating values, we were choosing action based on which action can maximize the reward that indirectly, implicitly also maximize the, we're choosing maximum value that implicitly also we're maximizing the reward function that we've defined also. So, and still they are good for many applications. So with studying policy gradient, we're not saying that so no one anymore should use those techniques. No, policy gradient has lots of benefits, but it's still those techniques that last week you've seen an example can work pretty good. On the other hand, now apart from value-based approaches, in policy-based approaches, we are going to learn the probability distribution over actions. That this can happen by getting the observation produced by stochastic policies. So what does it mean? You should think about this now to understand what is happening. I give you some time. Probability distribution over actions. So we have number of actions. We want to talk about probability distribution over actions. What was happening last week in deep reinforcement learning, we were bringing everything to form of probability as output of the neural network. Now we want to always bring everything on the form of probability distribution over actions. And we are getting observation and produce stochastic policies that you know now what is the stochastic and deterministic means that we discussed at the starting of the course this semester. So by looking at this, we can say we have ability to work in continuous action space without discretization. So it means that if you have a robot, for example, that this robot has like joints and gripper, in discrete, what we were telling, okay, we were saying that this revolute joint can have like 360-degree of rotation, for example. Then if I want to discretize it, I can define the action of this one in range of, for example, 0 and 360 degrees. And for only this joint, I have if I also have one resolution per degree, I have 360. And what if for this joint, if it's the same, then 360 times 360, if I want to discretize it, times, for example, if I have like something similar here too, because you have revolute joint that can be we can make it a linear movement by some mechanical components. Like we have again maybe 360 degrees there too. So you see that the action space can grow exponentially. But in continuous form, that also we will discuss it, we will see that, okay, instead of talking about discrete actions, we can talk about continuous form of representation of these actions so that policy gradient is the best option to help us to solve it. Basically the general idea is finding gradient of the change of the policy. That we will see how. So we will try to change the policy from one action to another action. It still can be discrete or continuous form, but we will see how we can calculate the gradient and how in continuous form we can use it. So we say value-based approaches are computationally very expensive if we want to use them in continuous space. Why? Because now I said I discretize this. Whatever it is, I can calculate the value function. But what if these are like infinity numbers or continuous form of, for example, 360 times the resolution that I have in, for example, dynamic cell motor, 28, I think, then each one of these will be grow again, even in discrete form, or if we consider it in continuous form with continuous calculations, then if you want to calculate the value base, the value function, it will be very computationally expensive. Why? Because of the equation that we calculated. If you look at the previous equation that we've learned to calculate with the learning concept, we had a part that in this part, we were getting the max of the next action. And getting of the max of the next action means that I need to know all individual action, next action, possible action, then get the maximum, although it's coming from neural network. So when you know this, it means that you need to know all these possibilities. And just if you want to get the max of all these possibilities, just one iteration is very expensive if it's continuous also. Then you have something like near to infinity number of the action space, then you want to get the max of that. That's why we say that we want to kind of see how with policy gradients we can replace this part, to get rid of this part, to update the policy, to update the value, to update the policy by the network by some parameterized value directly, not use the value function anymore. So here we have this the action value. We could have the techniques that has directly just using the value, state value. So is it clear so far? For everybody? So you need to know what's the problem that we are going to solve. The problem is over here with the value-based approaches, especially for continuous action space, or can be continuous observation to state space. So let's start to gradually see what we can do. We say we consider parameterized policy pi for a stochastic policy as pi theta, that this theta is parameterized value for us, for the network, the same definitions that we already have had for deep learning. Parameters theta that we want to find to optimize to find the best policy that we have. So usually what we use there, we usually use artificial neural network, but we are not limited to that. We can use, for example, logistic regression. If you are familiar with, you can formalize it, write some equations that do something similar than artificial neural network, especially if your problem is small and your action space is small, you can directly use it and you don't need to use neural network. But since now we have libraries, just 2 lines of code, everybody tries to also use neural network because here you need to do some math to do it. So again, the objective function is to maximize expected reward, similar to what we've had already. What was the expected reward? We were calculating expectation. So we want to maximize the expectation of the objective function that we have. That if you write the equation, it will look like something like this equation over here. What we want to do, we want to maximize the theta parameters of the expected policy that has the parameters of the neural network that we have, parameters of the value function approximation or network that we have. So we want to maximize theta expected policy that contains discounted reward, sum of the discounted reward over all trajectory. So trajectory means whole episode of one environment. We generate from time 0 to time t-1. We generate a trajectory, for example, robot moves in the environment. Then what we do, we gain some rewards. And our objective in policy gradient is maximize theta parameters by expected, maximizing this. But the problem is, we cannot, of course, use this equation directly because we said we want to work with policy directly, and we want to maximize the policy and calculate the policy. We will see how we can convert this equation somehow to bring the policy calculation inside calculation of the expectation over here. Is it clear? Any question? If you miss so far, then it will get harder to understand the rest. Make sure that you get the point. So I've written some notes here. It is a state action sequence in complete trajectory that is represented by T steps. So we have a trajectory, same discounted factor that we were discounting the reward, already have seen it. We want to calculate the discounted reward, sum of them, and expectation of policy, and maximize the theta parameters on the network. Now, this max over here, we are aiming to find the proper maximum parameters I mentioned to you. For example, neural network can do this for us. And that as I explained, this maximum expectation should finally result in maximizing the reward that we are collecting. That also, if we do this, if we maximize the policy parameters that maximize reward, we kind of improving the policy indirectly. Because if we do this, if we collect more reward, we are optimizing the policy directly there too, right? And finding best parameters to do that. Finding best parameters to collect the rewards that finally give us the policy that we want. So we can say this expected value can be computed by trajectories generated by policy pi that I explained already. Now, before moving forward, we need to have a look at the gradient ascent algorithm. I already explained gradient descent in deep neural network part. You know what is it now. I'm not going to explain it again. But What we are doing in gradient ascent algorithm, we are doing the same, exactly same, but we replace instead of moving downside of the hill, we want to move upside of the hill. The same scenario, we just want to ascend it. We want to increase the objective that we have. So it is called gradient ascent, and policy gradient is using gradient ascent because we want to maximize, not minimize. So now what we want to do, we say, okay, this term over here is the gradient of the parameters of the expected reward. With gradient ascent, if you remember, we were calculating gradient, amount of change gradient on the for example, one function, and we were minimizing. Here we want to maximize it. So if we can calculate the gradient of the expectation of this trajectory, so that we are kind of solving the problem. With this gradient, what we can do, with this gradient, we can update the weights themselves. So in neural network, in deep learning, what we were doing, we had some weights. We were calculating loss function by calculating some gradient and updating that loss function again. So the idea comes from there that if we can calculate the gradient of this term over here, then we can update the weights of the network that we have. So it kind of improves itself. So I've written the same thing there. Then we can update the parameters of theta of network in direction of the gradient that we have. And what we can do, we can write theta equal to theta, since we have gradient ascent added by learning rate alpha, gradient of the expectation of this term over here. So any questions so far? We haven't talked about the policy calculation and gradient of the policy calculation. We will see that part yet. But here we see that if we can calculate the gradient of this term, we can plug it to this term over here, add some learning rate of gradient, and update our network weights itself based on gradient and learning rate. So we have neural network. It needs the calculation of the weights. These weights can be calculated by adding each time the learning rate, how much I want to improve it, and the gradient of the trajectories expected reward. That we will see that also we can change this part a lot. We can, instead of having trajectory, we can use, for example, TD. We can use advantage. We can use different techniques over there. That can be replaceable. We will get to that part soon. But the whole gradient descent idea should be following this part. Gradient ascent, not descent. Gradient ascent and policy gradient. So I have an important golden point here that all the algorithms that follow in this update rule are called policy gradient techniques. All the family in the graph that on the tree that I showed you, all those family that are trying to do this scenario will call policy gradient, but their major difference is over here, and how we can update and how we can like kind of apply limitations or control the speed of convergence there, or whatever you're playing mostly is over that part. Because of that, understanding this part to this slide is crucial. Clear? Question? Okay. Now the question is how to calculate gradient from policy. So this is not easy at all. And if you want to answer that, we say we need to calculating gradient policy that is challenging. It depends on the selected actions directly determine the policy pi. So this policy pi with parameters theta is actually a network, neural network or deep network that generates one policy for me, right? And this policy pi is kind of depends on the selected actions that I have. And also, not only that one, but also it depends on the state distribution or transition probability that I have. That these two together, that also transition probability or state distribution comes from the policy pi that the same network is trying to give me what is the policy. At the beginning, of course, terrible policy, something random. But we want to kind of adjust those parameters to theta parameters in order to maximize the reward, in order to learn what to do. Agent learns what to do. So that these two elements are important parameters that we want to see how to deal with it and how policy gradient can solve our problem. Therefore, we say finding state distribution for the policy is very hard if environment is unknown. First of all, what does it mean? It means that for the selected action part, okay, we can say we are trying to select actions by the policy that we have. We can figure it out. But what about the state distribution? We don't know. In some techniques we discussed together, I gave you, for example, in the example, this is 0.7, this is 0.3, probability of the actions that can happen in the environment. Do we know that? We don't know that. Since we don't know that, we want to see, okay, actually how policy gradient is working and how trying to play with these values, with the state distribution in order to state probability distribution in order to solve the problem. So now we need to apply some mathematical calculations in order to bring the probability of the trajectory and the policy inside the game. And since we want to calculate the differences of the two policies and find a gradient, we need to use some policy gradient theorems that drives the objective functions, and kind of we have to remove this state distribution from directly calculating the objective, since we don't have it. So how this can happen, I'm going directly to the slide. So this term over here comes from the equation from policy gradient that I showed you. The sum of the expected sum of the discounted reward that we've seen. From there to come here, we have like 2-3 pages of math. I'm ignoring that. I'm letting for you to study it yourself. But finally, after doing all calculations, I think it's not necessary to know how that's happening, but you can have a look. I put the reference that you can have a look at chapter 13 of the book, how the derivatives comes, how we can remove that transition probability. Lots of mathematical knowledge requires, but finally we arrived this term over here. But let's see how it looked like and what is it doing. We say, okay, we are using similarly as previous, that we have the trajectory, and if we have using that trajectory in one episode, we are actually using Monte Carlo sampling. That we were in Monte Carlo sampling. What we were doing, if you remember, we were creating trajectory in the environment at the beginning, random, because policy is random. Then try to compute the policy gradient like this equation. How that is happening? If we use the equation in this form, we call the algorithm as reinforced algorithm, and let's see what is happening. we are calculating the gradient of the parameter theta on the network again. That is expected GT. GT was return. If you remember, we've seen how to calculate the return. But GT also, I stated over here, GT is equal to sum of the trajectory that we have by discounted reward of the next state and action. So this was the return that we always, a couple of times in different algorithms, we define it as GT. Then what we do, GT given by state T at for example, starting point is equal to sum of this return GT times gradient of the logarithm of the policy pi that represents state and action. So what does it mean? First of all, the logarithm over here, where is it coming? We didn't have it over there. The idea is just preventing exponential calculations that the numbers are growing, just taking them down, nothing very complex. We just want to bring the values. If we get the logarithm, the values are bigger. We rescaling and making them as smaller values. But here we have the probability that action A taken at state S with the parameter theta of the network. That actually this policy pi, I mentioned to you, we have a probability distribution. So that our network, neural network output should be something, right? That something shows the probability distribution that, for example, can be softmax. So that the policy parameter theta, action given by state, gives us the probability of the occurring that action in one particular state. So maybe it looks a little bit complex, but actually it is not, because here we have the probability of the one action that is occurring based on the softmax output. What was doing softmax, we're converting output of the deep neural network to probability forms. That's saying what is the probability of each one, and we consider that probability as output of softmax in form of probability of each action occurring in one state. Then calculate the gradient of the logarithm of that probability. Then multiply that by GT, discounted reward. Then we can calculate the expected reward of gradient descent algorithm that we have. Question? Any question? So I'm using all the terms that we studied during course. If you forget some, then you're missing some parts. We have to. So all the terms that we've used, like return, the probability distribution of the actions, and all the things, we have to use it here. Okay. Then what we need to do simply look at what's happening with that objective function. I can now update the same. This policy pi comes from network in the left side. This policy pi, the parameter theta can be updated by this term. The theta t added by 1, update of weights of the network, is equal to current weights of the network added by learning rate of the whatever learning rate should be, times sum of the discounted reward added by the same term, gradient of the logarithm of the probabilities that is coming from network. So we ask network, what is the probability of this action that is occurring? Then times it to the return, to sum of the return in this reinforced algorithm, then apply the learning rate and update our weights. I think this is the most clear thing that we can understand policy gradient technique. The network output in form of probability, calculate the gradient, then adding learning rate, then adding by updating our weights of the network. It's kind of asking network and updating itself. And why we can update itself correctly? Because of this GT. That GT is calculating discounted return, discounted reward for us. And this part over here is kind of feedback from environment. That this feedback from environment times the probability and the output from the network with some gradient can help us to update the parameters of network itself. Kind of, the policy gradient brings the benefits of the updating neural network that was updating theta into the game directly, into the equation directly. So merge the neural network update of the parameter theta into the also the calculating the policy and bring it to understand what's happening. Okay, this equation has different representation in different resources. You may need to a little bit study. You may need to be careful to see because I see more than 10 different form of representation of the reinforced algorithm. Now let's see step by step how reinforce is working, the algorithm. First of all, we have Monte Carlo policy gradient control that is episodic for policy policy pi action given by state and parameter. So here the theta parameters inside here, it could have been here too. It doesn't matter, it's the same representation. The objective is kind of finding the thetas that maximize action per state. So first of all, input is a differentiable policy parameters. We need to be careful also that the policy parameters are kind of defined somehow that is differentiable and that we can calculate the gradient. Mostly we can, but if you define it somehow that you cannot calculate the gradient or the gradient is not existing in some cases, you should reform it, define it somehow that is always calculatable. Be careful about that. So what is happening there? Another parameters, we have algorithm parameters like step size, learning rate, alpha, of course, should be greater than 0, otherwise our network won't learn. We have the initialization of the policy parameter theta, that we have initial weights of network. We have different approaches, for example, can be 0 or some random weights over there, whatever it is. We calculate, we initialize the parameters theta over there. And what we do next, first of all, in reinforced algorithm, first of all, we loop forever or for each episode. So forever means that, like, of course, it's sometimes in some case finished here because we have control. So so that when episode ends, that terminates. I mean the episode should end up in terminal state somewhere. So we generate episode for that one from state, the pairs of state action that goes to also reward, state action reward, and finally we have the state action reward. So this tree is a pair, and this tree is the end part that of course we have state t minus 1 because if its next state is terminal, we already finish it. Because of that, we don't need to calculate it again. As you've seen in the examples that we were, in the Monte Carlo approaches, we were generating and we were not calculating the end state, something similar. But reward of t is including that part over there. Then after that, after we generate this episode for reinforced algorithm, we loop for each step in the episode that comes from 0 to t minus 1. We want to move into the trajectory that we have. Then what we do? First of all, we calculate the return. GT is discounted, sum of the discounted rewards. The same term that I showed to you, exactly the same term. On the other hand, we have the update of parameters, theta added by 1, equal to same parameter again to update the theta parameter. So after understanding the math, the background, you see also the algorithm is pretty simple. Each time, for each episode, and for each step at the episode, we update the theta parameter. We update the weights of our network. And how that's coming from? That's coming from the calculate of the return, that is sum of the discounted reward, based on how based on the trajectory that you generated. If the trajectory is good, we get good return. If we get good return, then the gradient of the differences of that calculations shows that the gradient shows higher amount of change. And the change update of this data, not only by learning rate is defined, but also the gradient of the change. That the between policies and the policy, when we calculating the gradient in certain point, we can say how the slope is. And if the slope is higher based on this return, then the theta will be updated faster. And our network will move toward learning the collecting more return by GT that agent is doing in the environment. Clear? So this is kind of the base of the gradient algorithms. Whatever algorithm we have are kind of trying to follow this concept over here, but changing this part over there that I will introduce something. Here we have a note, we say reinforce is on policy. So why it is on policy? Why it is not on off policy? Because I stated over there the answer. The training samples are collected by target policy itself, by the policy that we have, same network. So whatever is generated by the policy also has been used to update the theta. And if the update step with the action generation step is same, then we said this is on policy. If they are different, they are off policy. But we are kind of maybe are more interested in if we have off policy. And we will see in next slide that we have another techniques that are off policy, and they are not using same network to do this, because when we are doing like asking same network what to do and updating the weights of same network, but what he's saying to do, then this can make instability in update of the parameters. He's like, I'm asking this student over here, Hugo, how you're performing. He says, good, I'm good. Again, how you're performing, good, I'm good. But we will see that it's not good. I should ask this guy how this guy is performing. Then you see they are fighting against each other. If you say bad, I'll be angry. Yeah, that's the Actor-Critic. That we will see. So we have a question that we say now, also let's have a look at how we can calculate the gradient from policy to maximize the reward if we have vanilla policy gradient algorithm. So vanilla policy gradient algorithm is very similar to reinforce, but some slight changes over here. Let's have a look at the term, how that looks like. So the return that we had there, here replaced by this term over here, that says, let me come from beginning. So we have gradient, we want to calculate gradient of the expected return on the trajectory. This tau here is trajectory that is generated by policy pi. Again, one network. And this is like the rewards of the trajectory that we have taught. So this is equal to calculation of the expected trajectory from policy pi, that in vanilla, instead of previous algorithm, we usually what to do? We usually calculate the 1 over size of the trajectory to get kind of the average of multiple episodes. Difference number 1. So here we want to get average. If you remember in Monte Carlo techniques, I was mentioning that the expectation usually is average. So it's the same thing. The expectation here of this policy is the average, 1 over size of the trajectory that I have. Times, so the average of this term over here, that says the same calculation that we had, the sum of the t from 0 to 3 minus 1, gradient of the logarithm of the policy pi. And the same definitions that we've had. Then here, instead of gt, we want to put this statement over here, that this statement instead says get total reward of the actions after the action that is happening. It means that instead of calculating from scratch from 0, we always calculate the discounted reward of the t prime equal to t. It means that when t is increasing, this is starting from next to forward view of the trajectory, not coming from the beginning. That we had different techniques of Monte Carlo, we're already familiar with it. So in reinforce, we did calculate based on the return, but here we calculate based on the oncoming actions in the trajectory, just looking forward of the trajectory. First, second, we get average. So this is called reinforce, the vanilla algorithm instead of reinforce. And what we do, again, we can update the parameters of the theta of network by the same process. Theta of the t added by 1 is equal to current weights of the network, learning rate times the average of the calculation, gradient of the logarithm of the probability that can come from different techniques. One is softmax of the network, then times the discounted reward of ongoing actions, oncoming actions of the trajectory. So again, vanilla is on policy, same as the reinforce. And now, as I mentioned to you, let's have a look what else we can do over there. The policy gradient technique of the update of the network weights is the same, but have a look what we can do. First of all, we've seen this as reinforce, total reward of actions. Then here we have the vanilla algorithm. So here just I put the return inside instead of GT. Then what else we have? We have very nice definition here as advantage function. Advantage function is one of the elements of also some advanced policy gradient techniques. For example, PPO is also using, some techniques also are using. So what does it say? It says that let's use benefits of both value and policy gradients. Use benefits of both kind of. What to do? Let's say the same term, similar term that we have expected return of the policy pi and some of the gradient of the logarithm of the policy pi based on the network and discounted. But here we have a new term that says calculate the Q of the SNT and subtract it by value of the ST. So here we have the value of the state. Here we have the each value per each action and subtract it from the value. That also is called, this part over called also baseline. What does it mean? I mean, this state, we've seen that we can calculate Q, and Q can state different values per each action, possible action. Which one is better or which one is good? The idea is here, not only use that one, but also calculate the value and subtract the Q of the action that we are taking in that stage by the value. So what does it says to us? It says we're getting some advantage. And what is the advantage of? If I know that being at this state has like 100 value, what is the advantage or differences of that action with this value, forward action, left action, back action? Kind of comparing the each values by that base value or baseline we call. So 2 times calculations, 1 time for state, the value, and 1 time calculating each one of the maximum of the, not maximum, each one of the values per action that are possible. Then we are kind of finding the difference. And that difference called advantage. Why? Because this is more stable. Okay, any question? So by looking at this, if you want to rewrite the equation to update the parameters theta, will be similar to previous ones. I didn't do that. Theta t added by 1 equal to theta added by learning rate. And after this, expected this term. So that now, instead of creating like trajectory like here or here, we say calculate the advantage and update the weights based on that advantage. So I have a note here. Let me see. A common variant of the reinforce is subtracting bias or baseline that I mentioned to you. This can be baseline. Also, there are many different techniques that this value can be replaced with anything else, but that's called baseline. A value, for example, advantage, that it reduces, kind of formally, we can say variance of the gradient estimation will be more stable. So it means that, the variance can represent the error. If you consider the distribution, the variance, how is wider, then our error is higher. So it is kind of tries to make it more stable or reduce the variance of the gradient so that it will be a useful advantage function. But also we will have a point over there too that we should be careful. Later, next slides, I will discuss about it. What else we can do? One of the techniques also is temporal difference. We can say, okay, let's calculate the residual temporal difference instead of Monte Carlo based creating trajectory, that we see that what was the reason we bring the temporal differences into game instead of Monte Carlo approaches. If you remember, in Monte Carlo approaches, we had to generate whole paths, then do whatever we want. But we said, okay, that's not good. Let's introduce TD. And we see TD0, TD lambda, the different techniques of TD. So the same scenario, the same motivation idea can come here. We can replace it with TD, temporal differences. The temporal differences of the value of the ST added by 1 or value of the ST. So what is the differences between this state and next state? In order to update the weights, in order to find out how good it is. This is not only limited to value, it can be Q value. But we need to then have modifications over there again. So the first part is same, gradient of the expectation policy, sum of the, again, gradient of the logarithm of the probability times discounted factor, and temporal differences. That the updates of the network is based on the how much each step, the state is, the value of each state is improving by temporal difference. So can we do something else? Can we use, instead of TD, this is TD0, right? This is TD0. Can we use another TD algorithms here? Yeah, you can do. You can replace any TD algorithm that we studied in specific chapter for that over here. Inside policy gradient technique. For example, we can have state action function that here we can say, okay, let's say after doing the same calculation, expected sum of the this term over here, finally, we can say Q of the state and action instead of value or temporal difference. We can directly also put the Q over there or TD of the Q over there in order to update the parameters. Clear? Question? Okay. Now we say we should be able to run the policy environment. So we have some points. We should be able, first of all, run the policy on the environment in order to calculate it, or in the simulation. That's of course obvious. It means that you need to define your algorithm kind of to be able to generate the action and run it over there. But also, in addition, we should represent the actions, as I mentioned, somehow that we can calculate the gradient of the policy over there. So update state, then we can calculate the policy gradient. But important point is that the policy gradient algorithm produced probabilities of actions, for example, using softmax at the end. That also we needed to know it in advance. I mentioned it before come to this point. One is softmax. We can do it, bring it the transition probability in any form that we can have. It's actually saying that what is the probability of happening that action as output with softmax. So given by states. Okay, so by knowing that background from policy gradient, by knowing two algorithms of the reinforced and vanilla, and seeing that how we can update the parameters, now we can have a look at one of the also famous algorithms of policy gradient, that the idea is, okay, we already knew policy-based techniques before today, with value-based techniques. We knew value-based techniques, but today we also have seen some techniques that is policy-based. Now, the question is, can we use both together? Can we use somehow the value and the policy to do the same procedure to use benefits of both? Yes, we can do, and that series of algorithms are called Actor-Critic. So we say using value function besides policy, we can update the policy updates better, and that method is approximating both policy and value function that called Actor-Critic. I already explained, and there are different versions of Actor-Critic. Too many different versions, actually, I can say. One of the basic and starting point of policy gradient is one-step Actor-Critic that is based on TD0 again, temporal difference is 0. We already studied, for example, Actor-Critic with eligibility trace. You know what is the eligibility trace? To update based on the trace of the backward or forward view of the value function. So that can be also part of Actor-Critic policy algorithm. You can bring it inside here. We can have like Actor-Critic with eligibility trace that is continuing. Is not like here we have finite horizon that episode ends somewhere. But in kind of tasks like prediction, your agent needs to do trading, and forever is like trading. Never episode finishes. The weather prediction, weather is not shutting down like after some episode. It's continuing. So in those kind of algorithms, also we can use eligibility trace of the Actor-Critic. So, and many others, you can have a look what we have. Here we have a point that I mentioned to you. We will have a look. This is a reinforced technique that we've seen. With baseline, the baseline that was advantage function is also learning both policy and the state value function together. So it was using the both terms together, but we should not be confused that it is not Actor-Critic. Those are different. What's the reason? Because we want to kind of create a criticization of the actor, that this criticization tries to improve the actor, not only calculating in one identical equation, something like baseline, because baseline has different versions. The advantage function is looking similar too, but baseline techniques are much more a better example for this one, that we should not mix them up. So what we have two networks in Actor-Critic. One network is called actor, another network is called critic. What is the actor? Actor is the policy, updating policy parameters theta, that is represented as policy pi state action, and critic is the value function. So here we have policy parameters directly that we were using for calculating gradient, but here is the value function that we already knew. Calculating the value of the state, how good each state is. So we split them. We're not splitting actually. We had it today. This one is like today we learned, right? We learned this one today. And this one we already knew. Like in deep Q learning, if we instead of Q put the value function instead of Q, then we have this one. So one network is for critic and calculating value function. Another network is calculating the policy parameters. Today's course as actor, and the value function approximation as critic network. Okay, clear? Now we need to see how these guys can work together. That's it. Merge them together in order to update it. But keep this in your mind. Whenever afterward you see theta, that before today's course we were talking about the policy pi theta. This theta parameters is referring to actor, and this W are again network parameters, but this is referring to critic parameters. So because they are different network, and of course their parameters and updates will be different too. Okay? So keep this in your mind. Try to keep it in your mind. We are moving forward. So we want to see now, okay, using that Actor-Critic directly how we can write the algorithm and how the equations looking like in order to have two networks of Actor-Critic in order to update the weights of the balls. But by the name, before I continue, also have a look here. Critic is criticization, kind of saying what to do, what not to do to actor. Keep this in your mind, that actor is generating the policy parameters, that policy finally is running in the environment, but critic uses some values in order to improve, in order to kind of advise the actor network. So based on that, let's have a look what is happening. Input is a differentiable policy parameters, policy pi, action, state, and theta. One input. And second one is differentiable state value function parameterization, that is stated as pi of action given by state and W. So actor, critic as initial values. And of course, we will have learning rate, and learning rate for both of the networks we will have alpha, learning rate alpha for network of actor, and the alpha for network of critic. Both must be greater than 0 because we want to learn, both networks must learn from the environment. Also, keep this in your mind. We have two pure random networks at the beginning. Both of them are trying to be learned. Both policy network and both actor network and critic network. At the beginning, they are 0, nothing knowing. how they are learning by getting some reward from environment and updating themselves, but trying to improve each other too. Okay. So what we do, first of all, we initialize the weights of the first network and initialize the second network. Parameters theta and w can be 0 again, or random values initialized again. We create a loop forever, similar to previous one, for each episode, and we initialize the state of the episode, first state. Keep this in your mind. This algorithm is online, and since it is online, we are not generating like Monte Carlo trajectory at the beginning. We're trying to update it in online way, because this technique also can be implemented similar to Monte Carlo. We create a variable I that is showing these steps, iteration kind of as one. Then we are creating a loop of the loop of each step in the episode. So episode, each step we want to one by one see what's happening. First of all, what we do, we need to take the action. Action from where? From policy network. What is the policy network? Actor network. How can I say? Because this parameter is over there, theta. And when I ask the network of the actor what to do, then it gives me action. Then I can run it. I can run action, observe next state of the environment, and get the reward. So far, very simple. Nothing special happened. Two networks, and I take the actions. I ask the act what to do, then I take it and see the next state. Now we want to see what's happening. All the Actor-Critic update is happening over here. First of all, we calculate the temporal differences error because the algorithm is online. If it's something else, we can calculate it differently based on written or whatever. Here, since it is temporal difference, what was the temporal difference? Predicted value. Why predicted value? Because it's network. When I told you, when we have network, we put hat here. Predicted network, predicted S prime and W subtracted by value of the S and W. So when we have W here, I'm asking critic network. From critic network that is in charge of answering me the value, I'm getting the values and calculating the differences of those values by giving this state and next state and saying what's the value, calculate it, discount it, add it by reward, and put it in another variable like delta. Clear? I calculated the TD error by value. Just have a point here that if next state is terminal, it means that it is finishing. Then the value of this S prime will be 0 because we don't have it. We cannot ask the network, right? That's not existing. You cannot ask non-existing thing. Then we say put it 0 over there, replace 0. Clear? We calculate the TD error first. Then we just have two steps, update of the parameters of the weights simply. What we do, the weights of the critic network, W is equal to, it would be better to show it as WT added by 1, but consider that new W's by previous W's. It is based on representation of, I think, the book that you have. As I remember, I brought it from them. So W, next weight is equal to current weight added by learning rate of the W, learning rate of the critic network that I define here, whatever it is, times the term that we discussed already. The I is representing the step size, the count that we are moving by some discount that we will see how to update it. The TD error that we calculated there, the delta. So TD error times gradient of the predicted value. That this predicted value gradient times the TD error, times the learning rate, and some one value of I that we will calculate down there can help us to update our critic weights, critic network weights. So that's also clear in understanding. The idea is very clear. I'm calculating by the reward and the error by TD that we've seen, for example, in many algorithms, how it's working TD. When I'm calculating that, I'm merging, I'm putting it into form of updating the weights that I have for network of critic. What about network of actor? We can do the same thing. Update of the parameters theta is equal to new theta, previous theta added by learning rate of actor network this time, times completely similar, but here we have logarithm of the value because we discussed in policy gradient. Here we have the, we are talking about the value, but here we are talking about the policy. So because of that, logarithm of the value of the action given by state and theta and the parameters that we have. I also have written there as a point for you that we are updating weight of actor network policy parameters, and it is relying on the gradient of the state from the critic network. Why state of the critic network? Because this value comes from critic network, right? But we are updating actor network. So this is the kind of connection between those two networks. This part over here, since comes from critic criticize actor over here. Says like old grandpa, like if I get old grandpa, maybe I'll be talkative. Oh, don't do that, don't do this, like that. That old grandpa is critic over there that criticize the network of the theta to update the weights. One more step, the I equal to discounted I. So this is discounted iteration that I have to in order to update the like fade the future rewards and future updates, because the weights of the like future and now should be differently applied on the weights of the network. That's why is because of that. Something similar what we do for the reward over here, discounted TD or discounted reward or discounted what we do. We are doing something similar on the each one of the weights. Any question? If this is clear, this is also based off the many advanced techniques. Also, it is also advanced technique, but also based on the many recent state-of-the-art techniques. Oh, what we have like state also comes to the next state. That's not very crucial. By knowing all of these, now let's have a look at PPO. After knowing all the course that we studied from the beginning, with looking PPO, we can simply define it. We don't need to do something extraordinary. We just need to have a look at the flow. And what is the idea? What is the idea? Let's see. First of all, the paper, original paper is over there, presented 2017. And we call it as Proximal Policy Optimization, one of the famous networks that we have. So what is the idea? Whole general idea says that in Actor-Critic, the parameter updates can be resulting in very big changes. The idea is that update of the thetas, the weights of the values of the network, suddenly, if you give a candy to a kid, will be very happy, forget even his mom or dad, right? Something similar can happen in those networks. If agent suddenly sees something good and gets big reward, forget everything whatever learned and says, okay, you are my God. The PPO basically says, okay, don't do that. Let's limit it. The whole idea is this. underline. So we want to add constraints to the size of policy update at each iteration. And what we do, if you look at the PPO, like transition policy optimization, that's also doing the same thing. The motivation is same, limiting the update of the theta parameters or alpha parameters of the networks. But here, 3PO is very complex to implement, very complex to understand. The procedure is like brutal. PPO just simplifies it and gives it like very short understanding of what's happening and implementation. So it is using the technique that does the limitations is named as a clipped surrogate objective that is similar to in the performance similar to PPO, as I mentioned. And there are different versions of the PPO, and in different scenarios they can be fail or success depending on what we are doing and the application that we have. But here today I'm going to just have a look at the general presentation of PPO, and as you are interested in, or if you want to do some research projects, you need to go to different versions of PPO and have a look which one is in the state of the art works are more successful. So we say we can compute the probability ratio between old and new policies. So one step is kind of say, okay, let's calculate the probability of the old and new and calculate the ratio. And the ratio can be shown as this one over here. Simply, we can say ratio of the parameter theta, update of the weights of the theta. This is not reward, this is ratio. That is the policy, the new parameters values for the policy that I have, and the old one, if I can calculate the ratio based on that, we can say, then we can write the objective function. An objective function can be like the error of the theta, that later also we can write again, theta is equal to theta added by this term over here, time equal to expected ratio that I calculate times the advantage of the state and action. An advantage we defined already, how it's look like. So now, but the problem is the idea that the main problem, the main challenge is that this theta can be updated dramatically. That, as I mentioned to you, the important part of the algorithm is doing this calculation. So what we do, we are trying to clip the amount of update on the theta. We say, okay, the same term, if you don't look at the whole equation, the same term over here of the ratio advantage function of the state and action. That advantage is equal to value subtracted by the Q, or Q subtracted by value. So what we want to do, we want to get the minimum of this term and this term, left side and right side. That left side is what we've done in the previous slide. But right side says, okay, if that is big, let's define some thresholding by writing one subtracted by epsilon and one added by epsilon. That this is kind of limiting our update of the weights that first of all, in this stage, we clip the term that we are calculating as original term. This term is original term of calculation. Here we clip it between -1 minus epsilon and 1 added by epsilon, usually is like 0.2. We clip it, and if this clipped version is smaller than the original one, because we want to limit it, we get the minimum. If this is okay, then use it. Otherwise, clip it. So if we clip it, then we are limiting our update of the network. Then we can write the L clipped. The loss of the clip is equal to theta. Then we can write theta is equal to theta added by this term. question? So with policy gradient, we clearly saw how we are updating the parameters weights. And here, just we want to a little bit change on the how calculating, but after calculating, the most important part is clipping, is to kind of creating trust region that how much update of the weight should be. If it suddenly see candy, say no, I love my dad and mom still. I don't want to change whole my beliefs. With this clip, we cut it. We put some rules. Okay, if somebody gives you $1 million, don't forget your mother and dad. See, these guys saying, no, we are going to forget it. Even we're going to forget you if there is $1 million. Okay. Nothing specific. After doing that, let's have a look at the diagram, how that is looking like. As I told you, it should be based on the Actor-Critic, and we have the environment over there. We have actor network, critic network. We have trajectory memories over here, but the point that we have over there is the clip, so that actor and critic was generating value, and actor generating the policy, right? And we calculating the ratio of policy, R of theta, with the equation that we said. We calculate the advantage. Advantage comes from value function, because advantage is differences of the values over there. Then we clip it with the equation of the previous slide. Then after we clipped it, what we do, we update our actor model over there. So this is the whole general idea. I hope I don't miss anything. We have mini back sampling over here. So with mini back sampling, of course, we already have seen it in deep neural network that we have memory of trajectories. We sample it, and the motivation is don't forget the previous weights. Don't just only update by current observation. Update also by previous trajectories that agent has seen for actor and critic model, and run it. And this is the paper. I think this paper represents this presentation of the Actor-Critic model that you, if you are interested in, you can have a look in more explanation how those are happening in more details. Then the general algorithm looks like this. Algorithm looks very simple for iteration 1 to unlimited here. Then for actor network 1 to n, run the policy in the environment at each one of the time steps, compute the advantage estimation, and after calculating the whole advantage in the loop, then optimize the surrogate L by cutting it, by limiting it, and update the parameters that we have for the network, and then bring the new parameters to the end and loop it. But this is the basic algorithm. Based on the different algorithms can be change a little bit. I told you we have different kinds of PPOs that they try to improve it and change some equations and flows. Here, let's have a look at the comparison of the PPO with other algorithms. Here, A to C is a version of the Actor-Critic. We have A to C added by trust region. Trust region is also trying to limit with something like PPO, and but it's based on trust region. It's another technique. We have CEM, we have PPO clip version that today we studied. We have vanilla policy gradient that also today we studied, and 3PO itself. And let's have a look at the performance. I think this is based on the Mojuko environment and 1 million time step of running the technique. So by looking at PPO, that is purple here, at the first example here, PPO is performing pretty better than the other one. Next best is the Actor-Critic. Then 3PO is down here. I don't know why, what happened to. Usually it works good. But I think that's because it's very complex, and you see it's still trying to converge. If we continue maybe 10 millions, maybe this guy comes up there, but this is low. Then in second environment, you can see that Hopper, another algorithm, again, PPO is working better. But the second one is vanilla that today we studied. Just let's have a look at two best ones. In the third example, PPO is better, and Actor-Critic with trust region is best. Here, almost they are doing well in inverted Pendelium from Mojuko. You have it in Isaac, not Isaac, OpenAI Gym simulations. We have richer problem here that again PPO is doing better. Vanilla second, vanilla policy gradient second. Here PPO is not doing well. Which one is 3PO is doing well in swimmer problem? You see, you have a problem that PPO is doing terrible almost. Not terrible in comparison to 3PO is worse. But here in Walker, again 3PO, again PPO is beating all others with large value, large amount of improvement. And I don't know, I should think what's the reason that is very different with the other techniques. Because I think in this problem, the reward function is like giving too many candies to kid. And they all are forgetting the weights of the updates. But 3PO is doing the same. And this one, the trust region is also doing the same. Trust region also creating a region of trust that only you can update the weights inside that trust region in something similar to clip but different. But yeah, I don't know why that's too much different anyway. So not only that one, we say PPO can be design choices for different parameterization, and the parameterization can be like here Gaussian. So the parameterization that we have can be Gaussian, not only that one. That policy pi can be represented in Gaussian form. The PPO parameterization can be based on the beta distribution. You remember beta distribution? You implement it. You did the examples. So PPO also can be implemented by beta distribution that we've solved already. Can be by softmax as output of the network that I stated many times. So these are representing the outputs of the distribution of the action that can be happen. And what does that mean? So in next slide, we are going to talk about the continuous action space. So far, whatever we explained, we mostly talked about the discrete actions, left, right, up, down, or the action space like this, 360 of the actions. But what if the action space we need to consider as continuous to solve it? Now we can answer it. Any idea from you guys? How we can bring the continuous action space actions into the game of the, for example, policy gradient? Students who are in Islam class should be easily answered. Because we did a lot with that concept in Islam. Okay, so this slide is also very important because it opens a new window to you that you can work with continuous action space. It means that if I'm solving the problem of industrial arm, instead of defining each joint as discrete actions, limited number of actions, I can consider as continuous and say this is action 1 in continuous form. This is action 2, this is action 3, then solve it in 3 continuous forms of the representation. With everything same, we don't need to change anything. We just need to, output of network should be changed somehow that I'm going to explain, then solve problem in form of continuous. How that can happen, we say, okay, Policy-based methods are practical way of dealing with large action spaces because they can consider continuous action space. In continuous spaces, we have infinity number of actions, even for one, and they are good options for policy gradient algorithms. And instead of computing probabilities of each action, we are learning a statistic of the probability of distribution. And what does it mean? It means that we need to have a look at Gaussian distribution. So if you remove Gaussian distribution, normal distribution from computer science robotics, we will fall down. That's very nice distribution. So what is happening with normal distribution? If anybody doesn't know, let's have a look. We can use it to describe the physical events, and they have different names for that: normal distribution, Gaussian distribution, or bell curve, and looks like this. Everybody are familiar, most likely, and we were doing a lot with it in Islam course this semester. We have the distribution that you can see. This is the normal distribution, and here in this variance between minus 2 pi and pi, we have 90%, 95% of probability. And what does it say? It says that if this is probability of occurring something, the probability of occurring, like in center, is higher. Here is lower. So we show it with mean. Mu is mean that shows where is the center of the distribution, probability distribution. So we have the meaning of the mean and meaning of the covariance over there, so that if we consider, we can represent the normal distribution with this term over here, the known term of the density probability P of x is equal to this term over here, that here we have the mean and here we have the covariance or standard deviation. What does it mean? It means that it says, okay, probability of happening something, mean says that is more likely here with how much error. This is mean and this is covariance. That's how much error and where is the probability of the happening. Now, before even continuing forward, let's say this joint over here that we have as a robot, so this is 0 to 360 degrees, if it's revolution. Then, if I can consider it as this part over here, then what can I do? This is continuous action space. Then I can show my action space by mean and covariance of what is the probability of the one action to happening over here. So that, for example, this is, if you consider rotational, like this is like 0, rotating 360, then we can say that, okay, here is the, for example, this action. And how we state it? We state it by the mean. And what is the error of the happening? So if that Gaussian distribution with mean and covariance can be adopted on the action space that I have, then I can do this one. The probability distribution function PDF can be rewritten as some weights of the neural network, so that we are trying to parameterize the mean and the covariance and the mean. Try to learn, find where the mean and covariance should be. This actuator will follow the mean. For example, where action should be performed, here, 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 here. I'm changing the probability and the covariance, how certain it is. The certainty is higher, more likely that is better action to do. So instead of learning whole action space, I just can learn two parameters, where the mean is, how much error is, and parameterize it. in terms of the policy action given by state and theta in form of normal distribution, Gaussian distribution, then solve my problem. Then the output of network will be something similar to per each action. If I consider normalized 0 to 1, for example, 0 to 1, then I can say per each action, for example, for this joint, I can just learn two parameters, mean and covariance, to say, well, what is the probability of that action happening so that my deep reinforcement learning or actor-critic network or policy gradient can learn it. Clear? So this is the general concept of bringing mean and standard deviation into game, and this is the term that can be used in order to do this. There are other different ways too, but this is one of the common ways to parameterizing function by adding the theta mu and theta mean to the representation of the action space. So what we studied today? Today we discussed the policy gradient and how we can directly improve the policy without calculating value first. Then we studied the reinforced and vanilla algorithms. We saw how they are performing as two policy gradient algorithms. After that, we discussed how we can use the benefits of both policy gradient and value function estimation together and put them together and introduce actor-critic algorithm. Then what we've done, we talked about the concept of continuous action space, and we saw that, okay, we can bring it into form of Gaussian distribution and action space. Whole unlimited number of actions can be represented by Gaussian distribution and change the error and the mean to estimate what to do at each time. And finally, how PPO is working and what is the general concept behind. If you have any question, feel free to ask. Okay, good. So today course is finished, and actually I was hoping